Hi everyone, this video is for section 4.6. The count in a bacteria culture was 700 after 15 minutes and 1500 after 30 minutes. Assuming the count grows exponentially, we have four different things that we want to uncover. One is what was the initial size of the culture? Two is find the doubling period. Three, find the population after 115 minutes. And finally, four, when will the population reach 11,000? So, to begin, in order to actually uncover the initial size of the culture, we need to create the exponential equation that we're going to use. So in this case, I would suggest starting off with your basic structure of a times b raised to the x. You could also use a times e raised to the rt, which would be assuming that you have a continuous exponential growth. Either one would be fine in order for you to make your predictions for this problem. So in either case, you should be able to uncover the same answers. But given this, what we want to do is we actually want to create two different coordinate points. One of which would be the after 15 minutes, we generate 700 bacteria. And then we also take another snapshot that says after 30 minutes, there is 1,500 bacteria. We're going to use these two coordinate points to help us uncover what our formula, or our equation in this case, should look like. So to begin, we can go ahead and say our output is going to be 700 times a, or is equal to a times b raised to the 15. Now, we can't go ahead and place any of this in for a, which is our initial value. A being the initial value means that what was the count at time 0? And b, we don't know the rate of growth in this case yet. We only know the input and the output. So after 15 minutes, we know that we have an output or an outcome of 700 bacteria. Now, there's really not much that we can do with this, so we need to go ahead and create a second equation. So we know that the output would be 1,500 is equal to a times b raised to the 30th power. So what we're going to go ahead and do is we're going to do a little bit of manipulation. So it looks like I can easily isolate the a, so I'm going to divide both sides by b to the 15th. This gives me a new definition. I know that a is the same thing as saying 700 divided by b to the 15th. So I can go ahead and substitute that in to my other equation. So now I have 1,500 is equal to 700 divided by b to the 15th times b to the 30th. So notice that we're slowly accomplishing a goal here. We're able to get rid of the variable a, and we can focus all of our attention on one variable. So to begin, we can go ahead and clean this up a little bit. And we can use our quotient rule, which would help us reduce this down. So in other words, if I have 30 b's in the numerator and 15 b's in the denominator, I can use my quotient rule, which is going to allow me to rewrite this line as 1,500 is equal to 700 times b to the 15th. So in other words, I did 30 minus the 15, which means that I have 15 b's left over. So we will go ahead and divide both sides by 700 to start isolating b. And that is going to give us 2.142857,143 is equal to b raised to the 15th. I understand that this number is not pretty. However, I did write out the full value that I got from my from my calculator because I don't want to round any of my values in the middle of my calculations. Rounding values while you're still actually arriving at an answer removes some of the accuracy of your work, and that potentially could throw off your answers in significant ways. So now we want to get b by itself, so in order to get rid of the power of 15 here, we're going to want to take a root. So I'm going to take the 15th root on both sides. And this is now going to reveal that b is equal to 1.05 2122273. The good news is now I can go ahead and uncover what my initial value is, or my A. I can substitute this value back in for B. Sorry, my arrow went a little bit haywire there. So I now know that A is equal to 700 divided by 1.0521222273, and we're going to raise that to the 15th power. This is going to reveal that we started off with 326.6 repeating bacteria. So this is our solution to the first question. To actually pull this a little bit further, we can actually say, okay, then the equation that I'm going to be using is y is equal to 326.6 repeating, which is my initial value, times 1.052122273 raised to the x power. So we would read this by saying we did start off with about 327 bacteria, and we were growing at about roughly 5% from that initial 100% of bacteria that we had. So let's move on to find the doubling period. So I'm going to show you the longer way in order to approach this one. Basically, we want to know at what time, so in other words, we're concerned about this x here, because if you recall from our coordinate points, x was representing the number of minutes that was passing by. We're concerned at what time are we going to see a doubling. So in other words, if I started off with 326.6 repeating bacteria, when am I going to see 653.3 repeating bacteria? Now you don't have to do this step that I'm about to show you, but again, I'm doing this more so that you can see the thought process. If I started anywhere else, it might seem like I'm starting in the middle and I'm leaving some stuff out, and I want to be as clear as possible. So in this case, we're going to go ahead and we're going to divide both sides by 326.6 repeating. And what you will find is that this is going to be equal to 2. So this shouldn't be shocking since we are talking about the doubling period. So for example, if we were asking about the tripling period, I should be able to perform that division and get a 3 in that case. So again, the 2 shouldn't be surprising when we get to this stage. So now my main issue here is that my variable that I'm trying to solve for is stuck in the exponent position. So I have to figure out a way in order to bring it down so I can actually work with it. And the answer to that is, well, in order to get the x to come down, we have a logarithm property that allows me to pull it down. So what I do to one side, I must do to the other. So I'm going to take the log of both sides, and that allows me to kick the x down. So if I were to write this fully, we would see that this is the log of 2 is equal to x times the log of 1.052122273. It's a fun number to say, isn't it, everyone? So at this point, we're almost done. We want to get x alone. So x is being held with the log by multiplication. So I need to undo the multiplication. So I will divide both sides by this logarithm. That will clear. And if we perform that division, we will get 13.6421, and then 2 repeating after that, is equal to x. And it is important to note that we want to note that this is in minutes. Okay, so basically, once we start observing this bacteria at time 0, or when we click our stopwatch to start counting, after 13 full minutes, the number of bacteria in our canister or petri dish or whatever will have doubled in size. Okay, so moving on. The second part of our question, or sorry, the The third part of our question is talking about find the population after 115 minutes. So I'm actually going to scoot this over so I have some access to some other information. So I want to work with this same equation that we came up with. And if we want to know what happens after 115 minutes, again, we are describing the x value, and we have that information. So now we're going to have y is equal to 326.6 repeating times our growth rate raised to 115 minutes. This will reveal how many bacteria we have after that amount of time has elapsed. So if you were to basically go into your calculator and punch this in, we would get 112,646.9643 bacteria. That's kind of gross, isn't it, everyone? Okay, and finally, to answer the last question, we want to determine when will the bacteria reach 11,000. So we need to ask ourselves, all right, what kind of information have I been given? And you can say, well, I have 11,000 bacteria. Then you can ask yourself, which variable does that apply to? Does that apply to x, or does that apply to y? And in this situation, it might be helpful for you to have already noted what your x variable is describing and what your y variable is describing. In this case, we know that the y variable is referring to the bacteria count, so it is going to go into the y position. We also, again, know that we initially started off with about 327 bacteria, and we also know the growth rate. So notice when we plug these values in, the only thing that we have left open is the variable x, which is what we're interested in. We want to know when will this population reach this count. So at this point, we are basically going to use some algebraic manipulation here to help us out. So to begin, I want to go ahead and divide the 326.6 repeating from both sides. Basically because notice that this is an easy thing to clear. It doesn't have any sort of exponents attached to it. There's no variables being added with it or anything along those lines. I can quickly do the division and clear it out. By doing that, we would get, undo. I want to make sure that I keep my colors in line. That division is going to result in 33.67346938. And again, note that I'm not rounding any of my values because I am in the middle of the calculation. I know it might be tedious to write all of this out, but if it leads to a more accurate number, that's what we want. I mean, the whole point behind mathematics is to be accurate, especially if you're not being asked to estimate anything. So this is what we have at this stage. And this is very similar to the work that we were doing with our doubling period just a few minutes ago. We would say, well, my x value, or my x variable, is stuck in that position. So in order to bring it down, I can use my logarithm property. And again, it's completely okay to put a log into your equation so long as you do it on both sides. What you do to one side, you must do to the other. This is why it's an equation, because we need to make sure that it stays balanced. So again, we would result in the log of 33.67346938 is equal to x times the log of 1.0521222273. It gets easier the more I write it. So now we want to go ahead and get x alone. So x is being multiplied with this entire logarithm. And again, note that the number, or the value that you're working with, is this entire logarithmic expression. It's not just the number on the inside. So I'm going to go ahead and divide both sides by this log to get x alone. That will clear. And then we would go to our calculator in order to help us actually get what this value is. And we're going to find that this is going to result in 69.21385.912 is equal to x. And again, we want to attach a unit of measurement to it. The number is useless if we don't know what it's describing. So since this is x, we know that that was referring to time. So basically, after a little bit past 69 minutes, we will have 11,000 bacteria sitting in that container. I hope that this was helpful. If you have any other questions, please let me know.